Hello everyone and welcome to my YouTube channel. I'm your host Trey and today we're going to talk about the IAS. Specifically, we're going to talk about the fetch and execution cycle within the IAS. If you're like me, uh, chances are that you're watching this video because you do not practically or technically understand how the instruction fetch and execution cycle works. So I'm here to make your life a little bit more easy. So before we get into the IAS, we just need to know a little bit more about the IAS because chances are you probably missed something with the IAS that um, typically won't make you understand what we're actually saying. So without further ado, let's get into our lesson. So, brief history with the IAS. The IAS, which is basically named after the Institute of Advanced Study Computer, also known as the IAS machine, is a historic computer architecture that was developed by the Institute of Advanced Study in Princeton, New Jersey, in the late 1940s, and it was completed in 1952. It played a significant role in the early history of computing and was influential in the development of subsequent computer architectures. What this statement basically means is that every computer that came after the IAS was modeled after the IAS, including this very computer that you're using, or the computer I'm using to record this video. So everything that we have, or every computer, or everything that we have here today that has the ability to do all the functionalities that we can do with a phone or with a PC or whatever is based off the IAS, because this was a revolutionary change that actually changed the entire computing world. So a brief overview of the IAS, because we're going to talk about, because this video is about the fetch and execution cycle, not a history lesson, right? So here's just a brief overview so that you get to understand. So we have design and architecture. The IAS computer was designed by mathematician and computer scientist John von Newman, along with a team of engineers, scientists including Julian Bigelow and Hermann Goldstein. It followed the von Neumann architecture, which is characterized by the use of a stored program concept, where instructions and data are stored in the same memory. This is a very important concept, or this is a very important key, because fun fact, the machines that came before the IAS used machine language, and machine language was basically binary code, and binary code was very, very difficult to implement and also to execute because it was very tiresome and all that. So von Neumann decided, hey, let me create a computer that already contains these instructions so that we don't have to manually reprogram the instruction or manually write the code over and over again, right? Basically, that's what he said. And when he thought of that idea, he came up with the stored program concept, and also the the revolutionization of computers or programming languages resulted into the creation of assembly language, which is the main language that the IAS is used for. The assembly language program that was, created basically uses or does away with the binary operation and uses mnemonics like load, add, subtract, and so on and so forth. So basically, the IAS is a stored program concept, so meaning it's able to store data and instructions in the same memory. Good. So the machine had a central processing unit, memory, and input and output components, right? Basic architecture or basic skeleton of the computers that we have today. Right? And the IAS computer had a binary electronic storage using cathode ray tube memory. And a little history of all this is that the IAS was in the second generation of computing. So this second generation of computing was using vacuum tubes to be able to have its processors and everything for the computer to actually work properly. It was using vacuum tubes, and it used specifically a cathode ray tube for memory. And it had a relatively small amount of memory by today's standards, with 4,096 words of 40 bits each. Right? We'll get into memory later on. But next up, we have a processing unit, and the CPU featured an arithmetic logic unit for performing So everything to do with arithmetics was done using the arithmetic logic unit. Simple, right? It's self-explanatory, and the instruction set architecture included instructions for basic arithmetics, condition branching, and memory operations. Okay, then finally we have the programming for the IAS itself. And the IAS computer was designed to execute stored programs, meaning that both instructions and data were stored in the same memory. Programs were written in machine language and assembly languages, were later developed to make programming more accessible. Like I said, the majority of the IAS was created using assembly languages. But assembly language was based off machine language because assembly language makes machine language way easier. And when this assembly language was developed, it made programming easier for programmers like you and I. All right, so let's get in deeper what memory actually is. So we said that the IAS consists of 4096 storage location called words, and these words contain 40 binary digits each, right? So now let's get into what binary digits are. Binary digits are also known as bits. So if you ever see bits, binary digits, it means the same thing. And each word has got 4096. Each word has got 40 bits where data and instructions are stored. These 40 bits are divided into two sets of instructions. So meaning we've got two sets of the instructions, and we have the left instruction and the right instruction. So we see that here we've divided everything. A plus 12 is equal to 20, and A plus 12 is equal to 20. 20 plus 20 equal to 40, and we have 40 bits of data and instructions stored. But now we have this type of scenario where it's divided into two instructions. We have the left instruction and the right instruction. And these instructions are also divided into two categories, each category being an opcode. Now, an opcode basically is 8 binary digits, right? If you don't know how to use binary, I highly suggest you check out my video on binary execution and binary arithmetic, binary operations, right? So opcode is basically 8 bits. So 8 bits that represents literally anything in the data world. So 8 bits, we have those, and then we also have our 12 bits that are address bits. So these address bits define the addresses that are there in the actual registers. Okay, good. So if you don't know what an opcode is, here's a better representation of an operation code. So an opcode is basically an operation code, if you did not know. And an opcode has got 8 bits. So we've got 128, 64, 32, 16, 8, 4, 2, 1. This is binary, and we can count how many bits we have here. We have 1, 2, 3, 4, 5, 6, 7, and 8. So everything here is in binary, and if you want to represent 1 in binary, we can just say 0, 0, 0, 0, 0, 0, 0, 1. That's 1 in binary. Again, if you don't understand how to operate using binary code, I highly suggest you watch my video on binary operations. Okay, so we have a sign and magnitude section where the first bit is always a sign bit, and then this guy determines the size of the actual value. Okay, so that being said, let's go into our final, let's just say our final information that we need to know. Okay, so we have registers, and registers are storage locations, and these storage locations consist of a program counter, which contains the address of the next instruction to be fetched from memory. We have the accumulator, which is employed to temporarily hold operands and results of the arithmetic logic unit operations. We got the memory buffer register, the MBR. This will contain the entirety of the contents fetched from the memory. We've got a memory address register, which contains and specifies the address, memory, or the instructions stored in the memory buffer register. And we've got the instruction buffer register, employed to temporarily store the right-hand instruction and its content. And finally, we have the instruction register. And this contains the operation code for the instruction that is being executed. So I highly suggest that you write this down because this is going to help you in understanding the fetch and execution cycle, what each register does and what its purpose is. So just copy this and write it down somewhere, and then we're going to refer it to execution and fetching cycle. Okay, so let's talk about the IAS instruction set. So the IAS instruction set, remember the IAS was written in assembly language, and this assembly language has got mnemonics like load, and we could jump, we could add, we could sub, we could multiply, we could divide, lift, shift, right shift, store, and whatnot, right? So this is basically assembly language, and this is the machine language that this one was derived from. The assembly language was derived from. So when we have our operation code here, and we have this operation code, when we execute this guy, or we have an instruction that is this, the computer will say, okay, load this, place it there, right? So basically we have this opcode, and this is the representation, and then the computer is going to do exactly what this is. So this is what the computer does. So you have this instruction set, and we're going to refer it to constantly, and we have this flowchart. So this flowchart, if you're like me, you probably didn't understand what this is, right? For me, I did not understand what this was when our lecturer was giving us this type of scenario. I did not understand what this meant, and I kept looking at it. I was like, what is this? What does this do? What is that? So I have basically simplified this entire process so that you understand what this means. And we can get it to like that, and we have this simplified uh, flowchart. So this is our fetch cycle, and our fetch cycle basically is going to start there. So you start your instructions there, and then we're going to look, is there any content in the memory buffer register? If not, then we directly map everything that is in the program counter into the memory address register. So meaning the memory address register is going to contain whatever is in the program counter. And the contents of the program counter, or sorry, the contents of the memory address register is going to directly be mapped into the memory buffer register, right? Great. So now that we have values in the memory buffer register, we do have those values, right? Are we executing the left-hand instruction or the right-hand instruction? So if we're executing the left-hand instruction, then we go to our memory buffer register. And in the memory buffer register, we say, okay, we get the right-hand instruction and place it in our instruction buffer register, right? And then after that, after we've done that, we go to our memory buffer register again and get the left-hand opcode and place it in our instruction register. And once we've done that again, we say, we go to our MBR again, we say the left-hand address goes into the memory address register. And then we start this whole process again. And then now, we still don't have, that's the fetch cycle, right? So in our execute cycle, we don't have anything in the memory buffer register, but we do have something in the memory address register. So meaning we can skip this step. And then we copy all the contents that are in the memory address register into the memory buffer register, right? And then we go to here and say, are we executing the left-hand instruction? If so, if not, because we're executing the right-hand instruction now, if not, then we say that the right-hand opcode goes into the instruction register from the memory buffer register. And because we already have an address in the memory address register, we skip this and then we increment the value by 1. And then we start this process over and over and over and over again. I hope that basically simplifies the whole process. But if you're a visual learner, don't worry, you're in luck, because I have the video and we're going to refer to this over and over and over again. So that being said, let's get into our actual example. So this is a fetch and execution cycle with our instructions and with our addresses there. So we're going to fill up these tables one by one so that you understand what's actually going on. So let's begin. So we have this instruction here, which is 05A. And if we go to our flowchart, our flowchart basically says that is there any content in the memory buffer register? Is there any content in the memory buffer register, right? So let's go back and check. There is no content in the memory buffer register. Okay, so if there's no content, we directly map everything that is in PC into memory address register. So we go here, memory address register is going to contain 058, right? Good. Step 2, get the contents of the memory address register and place them into the memory buffer register. So the contents of the memory address register is 05A. 05A is this instruction here. So we have 01, right? I'm going to put a space like so. And we're going to say 08A, right? Then we're going to slash it like so, so that we represent left and right. So we have 21, leave a space there, and we have 08B. So the reason why I've left spaces here is to be able to differentiate what are opcodes and what are addresses. And the reason I've put the slash there is because I want to differentiate between the left instruction and the right instruction. So we have that type of scenario like so. So now we'll go back to our flowchart and we say, are we executing the left-hand instruction? Yes, we are. So if we're executing the left-hand instruction, we have our MBR is going to contain the right-hand instruction. So MBR is going to contain the right-hand instruction. So meaning here, our right-hand instruction is going to be 21 space 08B. That is our IBR. And then if we go back to our flowchart, we have this next instruction that says, get the left-hand opcode and place it into the IBR from the memory buffer register. So we have that there, and in our instruction register, we're going to have this opcode. So we have 0, 1, like so. And because the accumulator doesn't have anything, so we're just going to leave it blank, like so. So notice that here we have 05A as well, because we are still executing this instruction, so meaning the program counter has not changed. So the program counter has not changed, meaning we are still in the execution cycle. So we're still in the fetch cycle, right? But now we are trying to execute this value. So now we say that we get our left-hand address and place it in the memory address register from the memory buffer register. So we look at that there, and then we say we get our left-hand opcode address, and place it into our memory address register. So this is 08A. So 08A like so, we have that. And then now we go back to our flowchart, right? Good. So is there any content in the memory buffer register? No. So if no is the answer, then we say that, okay, we got a program counter equals to memory address register. But because we already have a memory address register, we just skip this step, and then we say we get the contents of the memory address register and place them into the memory buffer register. So meaning we're going to get the contents that are in 08A and place them in MBR. And what are the contents of 08A? 08A has got the contents of this guy here. So meaning we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is our content for that guy. So now let's look at the instruction here. Our instruction is 01. If we were to look at our instruction set, we look for 01. 01 simply says that we transfer mx to the accumulator, right? So meaning we get our value in memory there and then place it into the accumulator. So we get our value that is currently in the address, meaning the memory address register, and take it to the accumulator. So our value is going to be AC is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have that. So we executed that instruction, and then we go to this guy here. Are we executing the left-hand instruction? Yeah, we are done with executing the left-hand instruction. So we're going to go to the this instruction here and say right-hand opcode is going to go to the instruction register. So the right-hand opcode is going to go to the instruction register, and our right-hand opcode is 21, like so, right? Good. So now we are done with this instruction. We are done with this 08A. So now we're going to go to this next instruction. So on the bottom there, we're just going to say 2108B. So let's just put a space there. So now that this instruction has been filled in. Basically, what fetch and execute means is say get, execute, get this, execute that, get this and execute it, get this and execute this. So we're saying get this, execute this, get this, execute it, get this, execute this, get this, execute this, get this, execute it. So meaning if we are getting something, right, we're gonna get this entire content, and then we are going to paste it there. That's what fetch and execute means. So the computer is going to say, okay, get this instruction, place it there, and execute it. So now that we have this instruction now, we're going to say, okay, great. Once we're done with all that, we increment the value by 1. Remember, we have this guy here, right? So our right hand opcode is going to be that, and then once we've put in our right hand opcode, if you can look at this properly, we put in our right hand opcode. Where is that? Our right hand opcode was placed in the instruction register, right? So we place our right hand opcode in the instruction register, which is there like so. And if we go back on top there, we have we've placed this guy, and then we say our instruction buffer register, our right hand address in the instruction buffer register is going to be equal to, or our memory address register is going to be equal to the right hand address. So our right hand address, memory address register is going to be equal to our right hand address. So this is going to be 08B, like so. And if this is 08B, we see this and we say once we're done with all this, we increment the value by 1. So meaning our program counter is going to equal to 05B, like so. Okay, so now that we have this instruction here, we go back to our flowchart, and I think I've made a mistake somewhere. It's MBRIR. So the right hand opcode in the memory buffer register, right hand opcode in the memory buffer register. So this guy is going to be 08A, right? Memory buffer register, right hand code, basically this is 2108B, right? So the instruction there is like so, but let's just leave it as FF like that. Oh, that's one too many, like so. So when we have the values like so, we are going to say, okay, now let's execute this instruction. So we're executing this instruction now, 21. So 21, if we were to go to our instruction set, 21 is basically this one. Where is this? It's this one. So transfer context of the accumulator to memory location X. So if we transfer all the content, our accumulator is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like so, right? And then now we start the entire cycle again. So let's go. Is there any content in the memory buffer register? No, there isn't. So meaning our because we already have a value in our memory address register, so we're just going to ignore this, and we're going to say contents of the memory address register is going to equal to the contents of the memory buffer register. So meaning whatever is in 08B is going to be placed here. So 08B is just going to have 8B because there's nothing in 08B, so just going to put that there. And then 08B is going to be as follows. And then we look at this. Are we executing the left hand instruction? No, we are not. We are executing the right hand instruction. So meaning our right hand opcode is going to be placed into the instruction register, like so. So our right hand opcode is going to be 21 there, and then because we don't have any other instructions left, our instructions are done, we close it like so. So that's just the first step. We've executed this guy. We are done, right? So now we go to 05B. Our program runner is 05B, and then we execute it like so. So once we've executed, once we've placed our 05B like so, we go back to our algorithm, and we say, is there any content in the memory buffer register? As we've seen, we don't have. So we say we copy the contents of the PC to the MAR. So we copy the contents of PC to MAR, which is 05B. But a memory address register has got 05B. 05B now, we're going to say our next instruction here, if you remember correctly, we say we copy the contents from MAR and place them into the memory buffer register. So the memory buffer register is going to contain the contents of 05B. What is 05B? We have the following: 02, 02, space, 05A, right? And then we separate it like that, and then we have 21, and then we separate it in 05B, like so. And then in our accumulator, because we have a value there, so it's just going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like so. And then now we go to our next instruction. So are we executing the left-hand instruction? Yes, we are. So if we're executing the left-hand instruction, then it means that we get our right-hand instruction and place it into the instruction buffer register. So we get 21 space 05B, like so. And then we go back to our algorithm and say we get our left-hand opcode and place it into our instruction register. So left-hand opcode is 02, like so. And we are done with that. So let's execute this scenario. So because we're executing this, we just say 05B, and then now our algorithm is saying that get the left-hand address and place it in the memory address register from the memory buffer register. So here we're going to say we're going to get the left-hand address, right? So the left-hand address is 05A. So 05A is 05A, like so. That's the left-hand address, right? Good. So now we go back to our flowchart, and our flowchart is basically saying that, is there any content in the memory buffer register? We know that we don't have any content there, so we say PC is equal to MAR. But because we already have a value in MAR, we leave that like so. And then we copy the contents of the MAR into the MBR, right? So meaning we copy the contents of this guy in here. So meaning we say that we put 01 space 08A slash 21 space 08B. So now we have our contents like so, right? That's our contents of our instruction. And then now 02 basically says, what does 02 say? 02, let's go to our instruction set, and 02 is this one, and it says transfer the negative value of the value that is in X into the accumulator. So we're just going to say negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like so, right? And once we place that like so, we go back to this guy here. Okay, so because we're still executing the left-hand instruction, we say that the memory buffer register, or the left-hand address, goes into the memory address register, right? And then we close that like so. So because we are still executing this guy, so the instruction buffer register still remains 2105B, and then our instruction register is going to contain 02, like so. Good. So now we have this guy, and then we copy and we paste it there. So now we are executing. So we fetched this data and we've put it there. So we have fetched this data and we have put it right there. So now let's try to execute this particular data. Great. So now our value is telling us, say that MAR is going to equal to our left hand address. So now our address in the left hand, which is equal to 08A, right? 08A. We are executing this 08A like so. So 08A is going to be like that, and now we're executing the right hand instruction, which is this guy here, because we're done with this one here. We're done with the left hand instruction. instruction. So now we're executing the right hand instruction, like so. So we go back here and we say, okay, PC equals to MAR. We already have a value in the memory address register. So we copy all the contents from the memory address register and place them into the memory buffer register, right? So what are the contents of 08A? 08A is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when we place that there, figuring out what we're executing here. So if we go back to this, we are saying that we are done with the left-hand instruction. Are we? We're done with our left-hand instruction, which is this guy. So we're executing our right-hand instruction. So if we're executing our right-hand instruction, we go back to this guy and we say, are we executing our right-hand instruction? No. Left-hand instruction? No, we are not. So meaning we're going to say our right-hand opcode is going to be placed into the instruction register. So our right-hand opcode is going to be placed into our instruction register, like so, which is 2-1. And then we're going to place in our instruction buffer register into the memory address register. But there's already a value in the memory address register. We leave it and then we increment our program counter. So we increment our program counter by 1, so meaning our program counter is going to be 05C. And we have that there. And because we are done with our instruction, we place a dot there or a dash to signify that we are done there. So also do that here. And to signify that we are done, we have that there. So we're only left with one slot, and this one slot has got this instruction 2-1, right? 2-1 basically means, what does 2-1 basically mean? Let's go to our instruction set, and 2-1 is this guy here. It means transfer the contents of the accumulator to memory location X. So whatever value is in the accumulator, place it into the memory location X. So let's just get what's in the accumulator, which is this one here, negative F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we are basically done with those two instructions. So that's how you go with the execution, fetch and execution cycle in the IAS. Basically something like so. So I just reviewed my instruction table as well, and I realized I made a mistake. Where it's supposed to be 20 to 1 here, it's supposed to be 0-2. Yes, I made an error. It's difficult to track these instructions, and we make mistakes. So here's a correction. It's supposed to be 0-2 in our instruction register, 0-2 there, and 0-2 there. But otherwise, everything else is exactly as the way it's supposed to be. So that's it for this video, and if you like this content, please do like and subscribe. It helps me out a lot. And if you want to learn more about binary code and everything, you can check out this video here. Please make sure to like and subscribe, and leave a comment if you want me to make more videos on computer architecture and organization. Otherwise, stay blessed, and I will see you in the next video. Take care.